Every time you click your mouse, type on your keyboard, or watch a video, every single one of those actions is being handled by one incredible little component, the Central Processing Unit, or CPU. It's this amazing piece of engineering that literally turns sand into a kind of intelligence. So today, we're going to pull back the curtain and see exactly how this thing actually works. So here's the plan. We're going to start by really understanding the CPU's role as the computer's brain. Then we'll dive deep into how it thinks, going all the way down to the microscopic little switches that do all the heavy lifting. We'll even see how those switches are built from, you guessed it, simple sand, before we wrap things up with the modern tricks that make today's CPUs so unbelievably fast. It's almost impossible to overstate just how important the CPU is. It's the command center, the engine, the decision maker for pretty much everything your computer does. Without it, your laptop or your phone is just a box of quiet, lifeless parts. So let's properly introduce our main character here. As the command center, it's really at the heart of, everything. It's kind of funny, isn't it? Such a simple definition for a device that's so incredibly complex. Because at its core, a CPU really only has one job: to follow instructions. The real magic is that it can follow billions of them every single second. But the CPU isn't a solo act, not by a long shot. It's more like the conductor of a huge orchestra. It's in constant, high-speed communication with all this other critical hardware, directing a non-stop conversation to make sure the job gets done. And to make all that happen, the CPU relies on a whole team. It uses these communication channels called buses to grab instructions from your system's main memory, the RAM. Now, inside the CPU itself, the control unit acts as a traffic cop, directing where all the information goes. For any math or logic, it turns to the ALU, the arithmetic logic unit, which is basically a super fast built-in calculator. And to hold whatever it's working on at that exact moment, it uses these tiny, ultra-fast memory spots called registers. Every single part has a specific, vital job. Okay, so with all these parts working together, how does the CPU actually process a program? Well, it all comes down to this fundamental, endlessly repeating cycle. It doesn't think the way we do, of course. There's no consciousness or creativity going on. Instead, it just follows this brutally efficient, relentless process, a kind of rhythm that dictates its every single move. And that rhythm is set by the clock signal. You can literally think of it as the computer's heartbeat. It's just a steady electrical pulse that keeps everything in perfect sync. So when you hear a CPU has a speed of, say, 4 gigahertz, that means its heart is beating an absolutely incredible 4 billion times every second. With every single beat of that clock, the CPU performs this little 4-step dance. It's called the fetch, decode, execute cycle. First, it fetches an instruction from memory. Then, the control unit decodes what that instruction is supposed to do. Next, it executes the command, maybe adds 2 numbers together. And finally, it stores the result. Then, a split second later, the whole dance starts all over again. And this diagram here, this shows you the physical path of that dance. You can actually see the instruction being fetched, then decoded, and then sent off for execution. It's a perfect picture of this little assembly line of computation, happening billions of times a second. Okay, so we've seen the process. Now let's zoom in. And I mean way, way in. What are the actual physical things inside the CPU that are doing all this fetching and decoding and executing? Just take a look at that number for a second. 30 million. What on earth could that possibly represent? That is how many transistors can fit on the head of a pin. And modern CPUs have billions of them. It's just mind-boggling. This is the magic of miniaturization, and it's what makes all of this possible. So what even is a transistor? Well, you can think of it as just a microscopic electronic switch. It has no moving parts. It can be flipped on or off billions of times per second with just a tiny zap of electricity. And this simple on or off state, this is the fundamental building block of all digital information. It's really that simple. When a transistor is on, it lets electricity flow through. We call that state a 1. When it's off, it blocks the electricity. We call that a 0. And by combining billions and billions of these simple ones and zeros, a CPU can represent anything. Any number, any letter, any instruction, and perform any calculation you can possibly imagine. Now, for what might just be the most incredible part of this whole story, how on earth do we build billions of switches that are so small you can't even see them? The answer, and you might not believe this, starts at the beach. The journey is just astonishing. It begins with simple quartz sand, which gets melted down and purified to an unbelievable 99.99999% purity. This ultra-pure silicon is then grown into a massive single crystal called an ingot. That ingot is then sliced into these razor-thin, perfectly polished silicon wafers. Then, in some of the cleanest rooms on the planet, a process using light and chemicals etches the circuits for billions of transistors onto each wafer. And finally, that wafer is diced up into the individual CPU chips or dies that power our entire world. But here's the thing. We can't just keep shrinking transistors forever. So to keep making CPUs faster, engineers have developed some absolutely brilliant architectural tricks. Let's look at two of the biggest ones, cores and cache. You see, the CPU is so blindingly fast that waiting for data from the main system memory, the RAM, is like an Olympic sprinter waiting for snail mail. It's a huge bottleneck. So to solve this, engineers built in CPU cache, a small, super fast bank of memory right there on the chip itself. It's like having sticky notes on your desk instead of having to run to the library for every single little fact. And to make this even more efficient, there isn't just one cache, but a whole hierarchy of them. You've got L1 cache, which is tiny but extremely fast, for data the CPU needs right this second. L2 is a bit bigger and acts as a backup. And then L3 is larger still and is shared across all the CPU's cores so they can all work together efficiently. It's a beautifully designed system to make sure there's as little waiting around as possible. And that brings us to cores. Early CPUs had just one core, which is kind of like having a single chef trying to cook a whole 5-course meal for 100 people. It can only do one thing at a time. A modern multi-core CPU, on the other hand, is like having a whole team of chefs in the kitchen. Each core is its own powerful processing unit, and that's exactly why you can stream music, browse the web, and type an email all at the same time without your computer grinding to a halt. And that really sums it all up, doesn't it? From a simple repeating cycle to billions and billions of switches built from sand, the CPU has evolved into one of the most complex and important inventions in human history. They are, quite literally, the foundation of our entire modern world.